All right, today we're going to be doing the last page of the salmon notes. The last page of the salmon notes. All right, so I have this lead sinker right here, and I put the lead sinker in a balance pan. I measure its mass, and the mass of the lead sinker is about 27 grams. Right? Now, water has a density of 1, so that means if I had 1 gram of water, that'd be 1 milliliter of water. Or if I had 10 milliliters of water, that'd be 10 grams of water. So 27 grams of water would be 27 milliliters. And this right here is a 25 milliliter beaker. So this is roughly around 27 grams of water right there. Now, there you have some boiling water. Okay. Now, if I were to fill this little flask up with the boiling water, I had 27 grams of boiling water, and I poured that into my hand, I would burn my hand quite badly. All right, I'd yell, scream, maybe cry. I would burn my hand pretty bad. However, my lead sinker right here, if I take my lead sinker and I place the lead sinker in the boiling water, now lead's a very good conductor of heat because it's very dense. The molecules are very close together. So the lead sinker is going to be the same temperature as that boiling water. It's going to be 100 degrees Celsius. If I take that and I now take it out of the water and I grab it in my hand like this. Now this is not comfortable by any means. However, I'm not burning my hand. Right? So 27 grams of that would burn me quite badly. 27 grams of that at 100 degrees would burn me quite badly. 27 grams of lead at 100 degrees, again, did not feel good, but it didn't burn my hand. Right? So what's different about them is they have, the lead and the water have different specific heats. Right? So specific heats, the amount of energy needed to raise the temperature of 1 gram of substance 1 degree Celsius. Now the energy in this case is what we're referring to as heat energy, and we measure the heat energy in joules. So I could say specific heat is the amount of heat energy in joules needed to raise the temperature 1 gram of substance 1 degree Celsius. Now, this chart right here is one that you can find, this chart here and this chart here are ones that you can find on the front page of your reference tables. All right, those two charts right there from your reference tables. Anyways, so what this means, it says granite has a specific heat of 0.79 joules per gram degree Celsius. What that means is if I had 1 gram of granite, and I wanted to raise that 1 gram of granite 1 degree Celsius, I'd have to add 0.79 joules of heat to it. Or with copper, if I had 1 gram of copper and I wanted to raise that copper 1 degree Celsius, I'd have to add 0.38 joules of heat to it. So, in other words, if I wanted to raise the heat of each of these 1 degree Celsius, I'd have to add about twice as much energy to the granite to get it up 1 degrees as I would to the copper. Now, that's granite and copper. Well, my experiment up here is dealing with lead and water. If I look at lead, it has specific heat of 0.13. Now, the thing with the biggest specific heat on this chart is water, which has a specific heat of 4.18 joules per gram degree Celsius. So if I do my math here, 4.18 divided by 0.13, the water specific heat is about 32 times higher than the specific heat of lead. That means if I want to make that water go up 1 degree, I'd have to add 32 times more energy than I would 1 gram of lead. All right. So I expand on that. If I'm raising the temperature up to 100 degrees, the boiling temperature, boiling water at 100 degrees has 32 times more energy in it than the lead at that same temperature. All right. Now, since I don't need very much energy to make the temperature of lead go up, lead has a low specific heat. It heats up very fast because a little bit of heat will make the temperature go up quite a bit. Whereas water has a big specific heat. It takes a lot of energy to make the temperature go up. So things with high specific heats up slowly. All right. Now, the flip side of that is once you get them to a high temperature, the water at 100 degrees has a lot more energy than the lead at 100 degrees. So when it comes time to cool them down, the lead doesn't have that much energy in it. So the temperature drops very quickly, where the water has a lot of energy in it. So it takes a long time to lose that energy, so it cools down at a much slower rate. So things with low specific heats, like the lead, they cool down very fast, where things with high specific heats, like the water, they cool down very slow. So if I had 100 grams of the boiling water and I poured that in my hand, it takes a long time for the water to cool down. So it's going to stay around that 100 degrees for a while, all the time burning my hand. Where the lead, because it only has 1/32 the amount of energy in it compared to that, when I pull out the boiling water, it's 100 degrees, but once I put it in my hand, it's only 100 degrees for a very short time. It starts cooling down very quickly. So those first couple seconds, I was kind of like, but then after that, it cooled down quite a bit, so I could hold it quite normal. All right. All right, so I take this and expand it to something you're going to experience more in nature. Let's say water and land. All right. Land is made of stuff like rocks. Granite is a rock, so we'll just say it's made out of granite. Specific heat 0.79. Water, specific heat over 4. So it takes about 5 or 6 times more energy to make the water go up 1 degree than the land. So during the day, the sun's giving off the energy. The land doesn't need as much energy to make the temperature go up. So the land's going to be hot, relatively hot. And since the water takes so much time and energy to make the temperature go up, it's going to be relatively cool. So the land heats up faster during the day than the water does. All right. Now it's like this during the day, but it's also like that during the year. In the wintertime, the water gets really cold in the wintertime. In the spring, it takes a long time for that to heat up. Now imagine a day like in, say, mid-May, all right? Usually temperatures in mid-May might be like, upper 60s or so. But it's not uncommon to get a day in the 80s in May as well. So let's say it's like May 15th and we get a day with like 80 degrees outside. You don't find a lot of people going up to Lake Ontario to go swimming, right? And the reason being is, even though the land might be 80 degrees, the water, because it has such a big specific heat, takes a long time to heat up. So the lake temperatures in the spring there are still going to be quite cold. So even though it's 80 here, you don't want to take a dip in the water because it's going to be so cold. So big bodies of water like the Great Lakes or even the Finger Lakes are pretty big bodies of water. So they take a long time to heat up and a long time to cool down. Now, a lot of the agriculture we have around here is based on this as well. Because the water takes a long time to heat up and a long time to cool down, it helps stabilize the temperatures. So up by Lake Ontario, there's lots of apple orchards up there. And the Finger Lakes, there's lots of vineyards for grapes. And one of the reasons why they grow them there is because, again, all the heat that's in the lakes that helps stabilizes the temperatures. All right. Next. All right, so right here, you can hear that there's ice water, ice with a bunch of ice cubes in it, or water with a bunch of ice cubes in it. Take the temperature of the ice water, and you can see that the temperature is right about 0 degrees. All right. Now, I take this and I put this on my hot plate and I let it heat up for a little bit, let's say roughly about a minute or so. And the hot plate is on high, so it's giving off lots of heat. All right, so it's been about a minute. It's been on the hot plate. Take the temperature of the water. And you can see that the temperature of the water is still pretty much right around 0 degrees. All right. So it was on the hot plate for a minute, lots of heat being given off of that hot plate, but the temperature of the water really didn't change at all. So that heat had to be used for something, all right? And what that heat was being used for was to melt the ice, all right? So as long as the ice is melting, the temperature of that water is not changing, all right? So that is what we refer to as latent heat, the energy absorbed or released during a phase change. All right. So let's say that over 0 degrees is the temperature at which water or ice melts. 100 degrees is the temperature at which water boils. So let's say I started off with some really cold ice. I had some ice at -10. And what I was doing to that ice is I was adding heat to it. Well, at -10, the water is going to be solid. It's going to be ice. And as I start applying heat to it, the first thing that's going to happen is not the ice melting, because if I'm starting off at -10, the ice doesn't melt until I get to 100, or 0 rather. So as I'm adding heat to it, what will happen is the temperature of the ice will go up, and then I get to 0, and then it's going to stay at 0 for a while. And that's what's happening with that beaker right there. All right. The reason why it's staying at 0 is because all the energy, all that heat I'm adding to it is being used to melt it, right? Because melting, I have to add heat to make melting take place. Melting is when I'm going from a solid to a liquid. Now, how much energy is required to melt? Heat gain during melting, 334 joules per gram. So for every gram of ice, I have to add 334 joules to it. Not to change the temperature, but just to go from a solid to a liquid. Now, once all the ice is melted, then I have liquid, and the temperature of that liquid is going to go up, 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 until I get to 100, and then it's going to level off again, right? So like when I had the water boiling at the beginning of the period, when I put the lead sinker in there, right, it was staying right at 100. And the reason why I was staying at 100 is because I was going through another phase change. I was vaporizing the water. And vaporizing is going from a liquid to a gas. And again, that's a process where I have to add heat to the water to make it happen. So how much energy I have to add to it, heat gain during vaporization, I have to add 2,260 joules per gram to make it vaporize. So it takes a lot more heat to vaporize water than it does to melt ice. So right now it is vaporizing, all right? and it's going to stay boiling, vaporizing at that 100 degrees for as long as there's water there. Now, if you imagine I took like a big balloon and put like a big balloon on top of that container of boiling water, and I had to trap all that water vapor, what would happen is as soon as all the liquid water was gone, then the temperature of that gas would go up, and I'd have like super hot water vapor. All right. So that's what happens if I add heat to water. All right. There's going to be these plateaus where the temperature doesn't change while it's undergoing a phase change. All right. But now let's go the other way. Let's say I started off with this big giant balloon of super hot water vapor. And what I did with that big giant balloon of super hot water vapor is I took that and I went to a freezer with it. All right. So that hot water vapor is going to be losing energy. All right. What's going to happen? Well, first thing that's going to happen, and so instead of adding energy, I'm taking energy away. So what's first going to happen is the temperature of that balloon of water vapor is going to go down, 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 down to 100. And then it's going to stay at 100 for a while it's undergoing condensation. Because during condensation, I'm going from a gas to a liquid. So right there, I'm going through condensation. Now, during condensation, the water loses energy. Heat's lost by the water. And how much energy is released during condensation is 2,260 joules per gram. All right, that's how much energy is being given off during condensation. So like when clouds form, all right, because clouds are made up of little tiny liquid water droplets, it takes condensation to make clouds, that's actually releasing energy to the atmosphere. And something like a hurricane, where there's lots and lots and lots of clouds forming, there's lots and lots of condensation happening, so there's lots of energy being given off to the atmosphere. All right. But anyway, so the gas is turning into liquid water, and as soon as again, I'm in a freezer with this balloon, as soon as all the gas is turning into liquid water, then the temperature of that liquid is going to go down, 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 so I get to 0, then it's going to stay at 0 for a while it's undergoing freezing, turning from a liquid to a solid. All right. That is also a process where the water loses heat, it's giving off heat. And heat released during freezing is 334 joules per gram. All right, so that's right here. It's going to level off while it is freezing. So while the water is freezing, it stays at 0. And then once all the water has turned into a solid, then the temperature of that solid can go back down. All right. So whenever there's a phase change, the temperature stays the same as either energy is being added to it or taken away. All right. That's latent heat, energy absorbed or released during the phase change. All right. Last thing I want to go over. Law of conservation of energy. In a closed system, the amount of heat lost by the heat source is equal to the amount gained by the heat sink. Energy cannot be created or destroyed. All right, so sample that. All right, so let's say I have a cup of coffee. And in that hot coffee, I drop an ice cube. Right? So the hot coffee is going to be the heat source. The ice cube is going to be the heat sink. Right? So let's say the hot coffee lost 100 joules of heat. Right? Now, heat's going to go from the hot coffee to the ice cube, from the heat source to the heat sink. But if the coffee lost like 100 joules, the ice cube might only get like 50 or so. And the reason being is there's other places for the water to lose, or there's other places for the coffee to lose heat. Now, some of the heat's going to be lost to the air, maybe 30 joules of that was lost to the air. There's going to be some heat that's going to get conducted through the sides of the mug. Maybe it's 20 joules of heat there. So it's not just that one place where the heat's going. A lot of heat's being lost to the atmosphere as well. That's an example of an open system. All right. Now, similar scenario, but instead of having a coffee mug, let's say I have one of these really super expensive thermoses by Yeti. A lot of these really expensive thermoses have double layers, and what they have between the layers is a vacuum. All right, so there's going to be a section there where there's nothing. They suck all the air out of it, and that makes it an extremely good insulator. And the reason being is, conduction takes place when molecules bang into each other, and if there's no air in there, there's no molecules in there, so you can't get any conduction. Or convection takes place with, when air or a liquid becomes warmer and less dense and rises and stuff. Well, again, there's nothing in there. It's a vacuum, so you're not going to get any heat transfer by convection either. So these kind of thermoses are extremely good insulators. Anyway, so let's say I have the hot coffee in there now, right? And I drop an ice cube in it. Now, if I lost 100 joules of heat, the ice cube would gain pretty much the 100 joules of heat. So there's no place else. The energy's not escaping any place else. So the amount of energy lost by the heat source is going to be equal to the amount gained by the heat sink. That is a closed system, all right? Because no energy is escaping it or no energy is getting into it. It's just all self-contained. The amount lost by the heat source is gained by the heat sink. In an open system, energy can be lost to the environment, or the environment could add energy to it. All right, that's the difference between the two. All right, so we'll be doing a couple labs dealing with this kind of stuff in the near future, and that is it.